But we do have to be able to move through our tree, and this is what I said before when we were talking about generic trees, that we need to make hard decisions on the ordering of nodes within a tree. And we can do this by just sort of deciding how we're going to move over a tree, right? Iterating over a list is sort of easy, right? You just kind of go next element, next element, next element, but trees are trickier for this reason. We can use this breadth first search or breadth first traversal algorithm if we want, where we add our root to a FIFO queue, and then while we haven't found the element we're looking for, we dequeue a node from that queue, and if that node isn't the desired element, we add the current node's children to the queue and go next, 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 next. This is sort of a linear equivalent to a tree search. I'm sorry, a linear equivalent to a tree search. This is sort of the linear equivalent in a tree of moving through your list. And you can see that because if we go left to right, which is not required, but not atypical either, what you can see here is if we have this tree, we're going to start with our root, right? We're going to go G, right? And if we're looking for H, we're not going to find G. So we go, okay, we pop something off our queue. We pop G off of our queue. And we go, okay, that's off of our queue. This is our queue. Right, and this is our order. Okay, what do we look at next? Well, we put its two children on, A and I. Okay, so now we'll pop something. We'll pop something off the queue. We'll dequeue something from the queue. Even I do that sometimes. We'll dequeue something from the two. We'll look at A. Well, A doesn't have what we're looking for. Okay, well, we'll put A's children on. Now we'll go to I, right? I comes off the queue. I gets dequeued. I's not what we're looking for. We're going to go F, then E, right? And then we go through all of these, and you can see we start here and we go across each level until we get to the element we're looking for. So that is nice, right? That's going to be useful for us. And we can, this can run efficiently, right? This is going to be big O of the number of edges plus the number of vertices, right? And for our tree, they're going to be the same because our number of edges is going to be number of vertices plus 1, right? So in a graph, these could be our extremes. But in a tree, this is really just going to be big O of the number of edges. It's memory intensive, and it's weak for deep nodes on wide trees. I tell you this because I want you to be able to look at algorithms and be able to understand them generally speaking. Do you need to worry about this for this class? No. You will see this again when you get to 233 essential algorithms. I have a feeling you'll spend some time on this guy.